Hello students, in this video lecture I am going to discuss the concept of Boolean polynomial functions. Now I have already discussed the concept of Boolean polynomial. Now in continuation with that we discuss the concept of Boolean polynomial function. Now let me just recall briefly what a Boolean polynomial is. Now when you consider a Boolean polynomial in two variables or two indeterminates or two unknowns, let's say the unknowns are let's say x and y, then a Boolean polynomial in two symbols, these x and y are called symbols or they can be called indeterminates or they can be called variables. Then a Boolean polynomial in two variables will be any combination of consisting of x, y, and then you can have x dash, y dash, and these may be combined with using the operators join and meet. So this is the operator for join and this is the operator for meet, which again I have discussed in my earlier videos. And the operator join can also be denoted by plus and the operator meet can also be denoted by dot. So if you consider an example of a Boolean polynomial having two variables x and y, then you can have something like this: x join x dash, then let's say meet y dash. This is a Boolean polynomial having two variables x and y. Then again you can have another Boolean polynomial, let's say x join y, and then you can put this in bracket and then meet x dash join y dash, something like this. So this is again a Boolean polynomial in two variables or two unknowns or two symbols x and y. So likewise, the way we have defined, the way we have considered a Boolean polynomial for two variables, similarly we can consider a Boolean polynomial for three variables. If the three variables are x, y, and z, then the Boolean polynomial can involve x, y, z. Also, it can involve x dash, y dash, z dash. It may or it may not involve these variables or symbols, and also these symbols are may be attached using the operator join and using the operator meet. Where, and as I said already, join can be represented by plus and meet can be represented by dot. So, which means that if you have a polynomial like this, which is a polynomial of two variables, then since join can be represented by plus and meet can be represented by dot, so you can represent this polynomial as x plus x dash into y dash. Here, whether you write or not dot, it's understood. So, I mean, you can write like this: x plus x dash y dash, like this. Then again, this particular polynomial which has two unknowns or two variables x and y, and then it has join and meet also. This can be represented by x plus y into x dash plus y dash, something like this. Here dot is there in between. So likewise, using these notations, polynomials can be written. You can have a Boolean polynomial involving two variables. You can have two variables or unknowns or indeterminates. You can have a Boolean polynomial involving three variables or unknowns or indeterminates. And then likewise, you can have Boolean polynomial. In general, you can have a Boolean polynomial involving n variables x1, x2 and so on till xn, which I have already defined in my earlier video. So now we have to come to the concept of Boolean polynomial function. Now if you are given a Boolean polynomial p and if you are given a Boolean algebra b, then you can always talk of Boolean polynomial function induced by the Boolean polynomial p over the Boolean algebra b. So to start with the concept of Boolean polynomial function, what you need is a Boolean polynomial over some set of variables or indeterminates or symbols, and you also need a Boolean algebra. So, and we always define a Boolean polynomial function which is induced by or which is corresponding to a given Boolean polynomial. So, we talk of a Boolean polynomial function induced by a Boolean polynomial p, or because of the Boolean polynomial p over some Boolean algebra b. So, these are the two things we always need in hand, that is a Boolean polynomial and a Boolean algebra before we start talking about the Boolean polynomial function. So, let me come now to what a Boolean polynomial function is, and then we'll proceed with an example to explain the whole concept. Now, coming to the concept of Boolean polynomial function, as I said, that whenever we are discussing the concept of Boolean polynomial function, we need two things before we discuss the concept of Boolean polynomial function. We need a Boolean polynomial P and we need a Boolean algebra B. So we always talk of a Boolean polynomial function induced by a Boolean polynomial P over a Boolean algebra B. Now, to make things simple, I will take a Boolean polynomial P, let's say over the set of two variables or two unknowns or two symbols, and let's say the two symbols are x and y. So, let me take a Boolean polynomial P to be, let's say, x y x plus x dash y x plus x y dash x dash. So actually this Boolean polynomial in terms of the join and the meet notation, this Boolean polynomial is just same as x meet y meet x, then join x dash meet y meet x, and then join x meet y dash meet x dash. So in terms of join and meet, the Boolean polynomial P can be written like this. Otherwise, to write the whole polynomial in a simplified manner, we can just write the Boolean polynomial like this, where plus would stand for join and dot, which is not which I am not writing over here, but it is understood that between the variables there is a dot symbol that we have. So this is actually x dot y dot x. So although we are not writing dot explicitly, but there is a dot in between. So this dot stands for the meet. So it is x meet y meet x or x dot y dot x. So likewise these terms can be interpreted. Now let me take my Boolean example, Boolean polynomial to be this as an example. Of course, we'll come to the generalized definition of a Boolean polynomial function. But before I come to the generalized concept of a Boolean polynomial function, I start the whole concept by taking a small example, and then of course we'll generalize the whole definition. So I'm taking a simple Boolean polynomial into variables or two unknowns or two symbols x and y. And although this again the Boolean algebra B, which I am taking in general, the Boolean algebra B can be anything. But to make things simple, I am taking my Boolean algebra B to be the simplest possible Boolean algebra consisting of two elements, and that Boolean algebra B is represented like this: B with a line, and that Boolean algebra is the Boolean algebra consisting of elements 0 and 1, which is in fact a chain of two elements. If you represent this Boolean algebra by a hash diagram, because I have already defined what a Boolean algebra is in my earlier video, and we know that a Boolean algebra is a complemented distributive lattice. What is the meaning of complemented? What is the meaning of distributive? And what is the meaning of lattice? This has already been defined in my earlier videos. So if one is interested in knowing more about these terms, you can just go and watch those videos. But the point is here, we are not interested in the definition of Boolean algebra. What the point which I am stressing on is that since we know that a lattice is a special type of PO set in which join and meet are defined. So in any case, a Boolean algebra is a PO set, and because a Boolean algebra is a PO set, you can always represent it using the hash diagram. So this particular Boolean algebra, which is the simplest Boolean algebra which I am taking, consisting of two elements 0 and 1, which is actually a chain of two elements. This can be this because it's a PO set, you can represent it as a PO set, or you can represent it using the hash diagram like this. So this is the hash diagram for the Boolean algebra B over Boolean algebra B having two elements. Now, as I already said that whenever you have to discuss the concept of Boolean polynomial function, then a Boolean polynomial function always corresponds to some Boolean polynomial P over some Boolean algebra B. So always before you start with the concept of Boolean polynomial function, there are two things which are required in hand before we even start discussing about Boolean polynomial function. One thing that you need is a Boolean polynomial, and the other thing that you need is a Boolean algebra. Now, to explain the whole concept with an example, I have taken my Boolean polynomial P to be this, which is a polynomial over two variables x and y, and I have taken my Boolean algebra B to be the simplest Boolean algebra consisting of two elements. Of course, we'll come to the generalized concept for the Boolean polynomial function, but just to give you an idea of what basically a Boolean polynomial function is, I have started off with a Boolean polynomial, and I have started off with the simplest Boolean algebra. Now, as far as a Boolean polynomial function is concerned, a Boolean polynomial function can always be imagined as a system consisting of a processing machine which processes values, and this processing machine uh, just depends upon the working of this processing machine depends upon what Boolean polynomial p you have taken. So how this machine will will depend upon what your Boolean polynomial p is. So in this particular case, my Boolean polynomial p is this. So I will see how my machine works. But you can always imagine your Boolean polynomial function as a kind of system consisting of a processing machine, where the working of the processing machine depends upon what is your Boolean polynomial p. And then now this machine has to be given some input, and this processing machine also gives out some output. The usual way the machines work, because machines always work in this way only. The general system is this, that you give some input to the machine, it gives out some output, and this is the way how a computer system also works. So you just have to imagine your Boolean polynomial function to be something like this, which consists of a processing machine, where the working of this processing machine depends upon what the Boolean polynomial p is, what Boolean polynomial you have taken. Then again, this machine has to be given some input, and this machine will give out some output. This input would depend upon what Boolean algebra b you have taken, and this output will also depend upon what Boolean algebra b you have taken. So this whole system will actually, this whole system or this whole structure would actually represent a Boolean polynomial function. Now, how the Boolean polynomial function actually works, mathematical definition, of course, we'll come to that, but let me show you through a model which I have made, a small model to show how a Boolean polynomial function actually works. And the Boolean polynomial which I'll be taking in that model would be this, and the Boolean algebra B that I would be taking would be Boolean algebra, the simplest Boolean algebra, consisting of two elements, which is a chain of two elements with 0 at the bottom and 1 at the top. So let me start just explaining that concept through the model. Now, as I said that the Boolean polynomial function can be thought of as a sort of a system consisting of a processing machine in which takes in input and which gives output. So, the Boolean polynomial which we had taken was xyx plus x dash yx plus x y dash x dash. So, this is the Boolean polynomial that we had taken, and I am going to take my Boolean polynomial p in the processing machine. So this is your x, then you have y, and then you have x, and then there was a plus sign, and then x dash, and then y, and then x, and then a plus sign again, and then x, and then y dash, and then x dash. This was my Boolean polynomial p, and now I put this Boolean polynomial p in this processing machine, and now depending upon whether we are using x or we are using y, or whether we are using x dash or whether we are using y dash, the values which the input values will be taken accordingly. Now, because this Boolean polynomial, one thing which you have to remember is, because this Boolean polynomial p which you have x y x plus x dash y x plus x y dash x dash, this Boolean polynomial p which we have taken, this is a Boolean polynomial in two variables x and y. So you have to give, there are two types of inputs that will go, and the input machine that I'm taking is this one. This is the input machine, and here this would correspond to the values of x, this would correspond to the values of y. And now, because we have taken our Boolean algebra to be b, and b has two elements 0 and 1, so the variable x, the first column corresponds to the first column corresponds to the column for x, and the second column corresponds to the column for y, and x can take values from the Boolean algebra b, and y can also take values from the Boolean algebra B, and we know that the Boolean algebra B, which we have taken the simplest Boolean algebra, that Boolean algebra consists of two elements 0 and 1. So this x can also take values from 0 and 1, this y can also take values from 0 and 1. So let us see what are the various possibilities that x and y can have, the input, what are the different types of input that you can have. So as I said that this is the column for x and this is the column for y. So I put x in the first column. So this is the column for x, and then there is a y over here. And then now, because the values of x will come from the Boolean algebra B, which consists of two elements 0 and 1, and the values of y will also come from the Boolean algebra B, which has two elements 0 and 1. So the various possibilities for x and y can be that it can happen that both of them are taking values 0 and 0. So 0 0 is one possibility, that x is also 0 and y is also 0. So 0 0. The other possibility is that again x is 0 and y is 1. So 0 1. This is another possibility. Then the third possibility is that it can be 1 0, which means that x can be 1 and y can be 0, and the last possibility is that x can be 1 and y can also be 1. So these are the four possibilities, because the possible values which x can take are 0 and 1, which means there are two possibilities for x, and the possible values for y are again 0 and 1, which are two possibilities for y. So 2 into 2, which means four possibilities, and these are the four possibilities. 0 0, x and y x and y together can be 0 0 or 0 1 respectively, or 1 0 respectively, or 1 1 respectively. And when you're actually writing the values are written like this: 0 0 1 1 in the first column, and then 0 1 0 1 in the second column. So these are the possibilities, these are the input values which you can have. And now this is the polynomial which we had, polynomial p, that we had taken: x y x plus x dash y x plus x y dash x dash. Let me see what are the different values now. Again, x, of course, x will take values according to this row. In this row, the values of x and y will be according to this pair of values of x and y. In this row, again, the values of x and y will be according to this row. In this row, the values of x and y will be according to this row, and in this row again the values of x and y will be according to this row. And as far as x dash and y dash are concerned, if x is 0, then x dash will be, the value of x dash will be 1. If x is 1, then the value of x dash will be 0. Same goes for y. If the value of y is 0, then y dash will be 1, and if y is 1, then y dash will be 0. It's just because x and x dash, the variable and its complement, they are opposite of each other. So we know that in the Boolean algebra B, if x is taking value 0, then x dash takes 1 and value 1, and if x takes value 1, then x dash takes value 0. So I mean, it's opposite basically. So this is how, let me now, when we know that these are the values of x and y, let me just put these values corresponding to these possibilities of x and y. Let me put the values over here, and then we'll find out what is the final output, final value of this polynomial, depending upon what are the values of x and y and x dash and y dash in this polynomial, and by using rules of Boolean algebra, we'll find out the final values.
So let me put the values of x, y, x dash, y dash in this particular polynomial for this combination of values of x and y. Here x is 0 and y is 0. So I put the values one by one. So this x is 0 and this y is 0. This x is again 0, and then there is a plus sign. There is a plus sign in between, and then x dash. Now when x is 0, then x dash is 1. So I put the value of x dash as 1. Then y is 0, x is 0. Then again there is a plus sign. Plus means join. And then again x is 0. And now because the value of y has been put as 0, you can see with that y is 0. So y dash is 1. So I put the value of y dash as 1. Again, because the value of x is 0 over here, so x dash correspondingly will be 1. So these are the values for the first pair of values of x and y. When x is 0 and y is 0, we put the values in the polynomial. The same thing we do for this combination of values of x and y. When x is 0, y is 1, and when x is 1 and y is 0, and when x is 1 and y is 1, we fill up all these gaps and we write the value of the polynomial, and then finally we will find the output for each particular row, and we will find out using the rules of Boolean algebra what is the output corresponding to each set of values. So again, for the second combination of values of x and y, when x is 0 and y is 1, then let us put the values for this polynomial. And the values are for x 0, this is going to be 0, then y is 1, so y is 1, and then x is 0 again, so 0, and then a plus sign, and then because x is 0, x dash is 1, so the value of x dash is 1, y is 1, the value of y is 1, and then x is 0, and then a plus sign, x is 0 again, and then y, because y is 1, so y dash is 0, and because x is 0, x dash is 1. So this is for the second row. Similarly, for the third and the fourth row, we'll take x as 1 and x dash as 0, and y as 0 and y dash as 1. And for the fourth row, for x is equal to 1 and y is equal to 1, in this particular row, x dash will be taken as 0 and y dash will be taken as 0. So I'll just complete these two rows. So we have seen that corresponding to these inputs for the two variables x and y, because they're in the given polynomial p, which we said that can be imagined as a processing machine. So corresponding to this polynomial in two variables x and y, the variables x and y have been given inputs, and x we have seen can take values from the Boolean algebra B consisting of two elements 0 and 1. Similarly, y can take values from the Boolean algebra B consisting of two elements 0 and 1, and correspondingly we have written all the values of x, y, x dash, y dash, and we have substituted all the values over here. Now using the rules of Boolean algebra, we can just find out the what is the final answer, what is the value of this polynomial that we get, and the output can be written correspondingly in this particular sort of machine, which will be behaving like a output machine. So basically this is the processing machine, this is the polynomial, and these are the values that have been put in the polynomial, and so the polynomial behaves like a processing machine. Input has been given to the polynomial using the values of x and y. So basically the input is in the form of ordered pairs. Now because there are two variables x and y in the given polynomial, so there will be two inputs, one for x, the other for y, and the input for x will come from the Boolean algebra B, the input for y will come from the Boolean algebra B. So in a way the input comes from B cross B, because there are four, because the input is in the form of ordered pairs and there are four ordered pairs, and B, which is the set consisting of two elements, the Boolean algebra B consists of 0 and 1. So B cross B will have four elements as its order, four ordered pairs as its elements. So these are the four ordered pairs: 0, 0, 0, 1, 1, 0 and 1, 1. So B cross B is the input, and the polynomial is behaving like a processing machine. And again, one thing which we can note from here is that here there are two variables, so the input is in the form of b cross b. If there would have been three variables x, y and z, the input would have been in the form of three variables. If the three variables are x, y and z, then here the input would have been x, one column for x, the other column for y, and the third one for z. So the input would have been in the form of b cross b cross b, b multiplied with itself 3 times. If there are 4 variables, then the input will be in the form of b cross b cross b cross b. 4 times you have to multiply b with itself, which means that depending upon the number of variables over here, the input accordingly, the input will the form of the input will be according to that. If there are 2 variables, then the input will be from the set b cross b. If there are 3 variables, the input will be from b cross b cross b. If there are 4 variables, the input will be b cross b cross b cross b, which means b to the power 4, which means that in general, if there are n variables in the Boolean polynomial p, which you are imagining as a processing machine, then the input machine will have input b to the power n, which means b cross b cross b and so on, b multiplied with itself n times. So you have to multiply b with itself as many times as many variables are there in the Boolean polynomial. So this was one thing. And now coming to what is the output in each case. So let me evaluate each row one by one using the rules of Boolean algebra. Now 0 dot 0 dot 0, which means 0 meets 0 meets 0 is 0. Then 1 dot 0 dot 0, which means 1 meet 0 meets 0 is 0. And 0 dot 1 dot 1, which means 0 meet 1 meet 1. This is also 0. Whenever there is a 0 in between the meets, then the answer is always 0. So this is 0, this is 0, this is 0, and 0 plus 0 plus 0, which means 0 join 0 join 0 is again 0. So the whole answer comes out to be 0. This is just using the rules of the Boolean algebra. So corresponding to the first row, the output is 0. I have put the output over here. This you can imagine is sort of output machine. Then again this is 0, this is also 0, and this is 0. So 0 plus 0, 0 plus 0 plus 0, which means 0 join, this plus is same as join. So 0 join 0 join 0 is again 0 using the rules of Boolean algebra. So again the output corresponding to this row will be 0. And again this is 0, this is or this whole 1 dot 0 dot 1 is 0, 0 dot 0 dot 1 is again 0, 1 dot 1 dot 0 is again 0, and 0 plus 0 plus 0, which means 0 join 0 join 0 is again 0. So again the output is 0. So I put a 0 over here. And then 1 dot 1 dot 1, which means 1 meet 1, the value is 1 using the rules of Boolean algebra. Plus again we have 0 dot 1 dot 1, the value of, because there is a 0 in between, so 0 dot 1 dot 1 is 0 meets 1 meet 1, which is again 0. And this again, because there are 2 zeros, so 1 dot 0 dot 0, which is 1 meet 0 meet 0, this is again 0. So this is 1 plus 0 plus 0, this whole thing becomes 1 because there is a 1 over here, and whenever there is a 1 in the join, so this is 1 join 1 plus 0 plus 0, 1 plus 0 plus 0, or 1 join 0 join 0. And using the rules of Boolean algebra, because there is a 1 in the join, so the value of this whole expression is going to be 1. So this is the output that we have. Finally the output has been put in the output we get from a machine. So you can visualize this whole structure, this whole system which we have made, consisting of 3 parts. One is the processing machine, which is nothing but the Boolean polynomial. The other is the input machine, in which you have the inputs, and then is the output machine, which will give you the outputs. And the processing machine, the working of the processing machine depends upon what is the form of the Boolean polynomial that you have taken. If it is a Boolean polynomial with 2 variables, then accordingly the input machine will have 2 columns, and each column will take values from because we are talking of Boolean polynomial function over the Boolean algebra B, where B we have taken to be the Boolean algebra consisting of two elements 0 and 1. So the input for the first variable will come from B, for the second variable will also come from B, which means that the input will be in the form of ordered pairs. So the input will be in the form of B cross B. So if this is a Boolean polynomial with two variables, then you have to take the input from B cross B, which means you have to multiply B with itself 2 times. If this is a Boolean polynomial in 3 variables, then the input will be B to the power 3, B cross B cross B. And if this is a Boolean, so if this is a polynomial having n variables, then of course the input will come from the set b to the power n, which means b multiplied with itself n times. So again also we can see that the output again is from the Boolean algebra B consisting of two elements 0 and 1. So the input in this case, in this particular case, when we have taken our polynomial, Boolean polynomial to be a polynomial over two variables, then the input is from B cross B and the output is again in B. So this whole system, this whole structure can be imagined, this whole structure which consists of the processing machine, which is the Boolean polynomial, the input machine in which inputs for the variables x and y are given, and the output machine which gives you the output. This whole structure can be imagined as a Boolean polynomial function, where a Boolean polynomial function is nothing but it is a map or a mapping whose domain is depends upon what is the Boolean polynomial that has been taken. If it is a Boolean polynomial with two variables, then the domain will be B cross B, where B is the Boolean algebra that we have taken. In this particular case, the Boolean algebra was taken to be the Boolean algebra consisting of two elements only, 0 and 1, but in general any Boolean algebra can be taken. So the domain will be B cross B, and the range finally will be again in the same Boolean algebra B that we have taken in the beginning. So this whole processing, this whole structure or the system can be imagined as something consisting of input, processing and output, that is input machine, processing machine and output machine, or it can be regarded as a mapping whose domain is from B cross B and the range is also in B. So this is the whole structure of a Boolean polynomial function. So this was a model which describes a Boolean polynomial function, and now I'll mathematically give the definition of Boolean polynomial function based on what we have seen in this particular structure. Now, the example which we had just taken for a Boolean polynomial, that was a specific example in which the Boolean polynomial P was taken to be xyx plus x dash yx plus xy dash x dash, and the Boolean algebra that we had taken was a specific Boolean algebra B consisting of two elements 0 and 1, and we had seen that corresponding to this Boolean polynomial P and this Boolean algebra B, the Boolean polynomial function which we can denote by P bar B came out to be a function mapping from B square to B. B square came because the Boolean polynomial P is defined over two symbols x and y. So in the domain B has to be multiplied with itself as many times as many symbols are there. So P bar B, which is the Boolean polynomial function corresponding to the Boolean polynomial P over the Boolean algebra B, or P bar B, which is the Boolean polynomial function induced by the Boolean polynomial P over the Boolean algebra B. This came out to be a function mapping from B square to B. And the B square, which is the Cartesian product of B with itself, consisted of all ordered pairs of the type A1, A2, where the first component A1 comes from B and the second component A2 comes from B, where capital B is a Boolean algebra consisting of 0 and 1, which means that first component we had seen that this has possibilities of taking value 0 or 1, and A2 also has possibility of taking value 0 or 1, which means that there are four possible ordered pairs which we had seen, that 0 0 0 1 1 0 and 1 1, which were present in B square, and corresponding to each ordered pair we had obtained a value for the Boolean polynomial function. P bar 0 0 had a value, P bar 0 1 had a value, P bar B 1 0 had a value, and p bar this b1 was also calculated. So these values were calculated as 0 0 0 1. So basically the whole function p bar b, which is the Boolean polynomial function, could be determined, and how these values were obtained, that was also explained while we were discussing the example. For example, this p bar b 0 0, this the image of 0 0, the ordered pair 0 0 was obtained by replacing the first because the first component is 0 and the second component is 0. So in the Boolean polynomial p, x was replaced by 0, that is the first component, and y was replaced by 0, the second component, and accordingly x dash which would become 0 dash, which is the complement of 0, would be replaced by 1, and y dash, which would be 0 dash, would take value 1, because again 0 dash is 1 in the Boolean algebra B, and wherever 1 dash came, that was replaced by 0 in finding out these values. So all, and using the rules of Boolean algebra, these values were calculated. So the whole Boolean polynomial function p bar b could be determined if the Boolean polynomial p is given and the Boolean algebra B is given. So this was just a specific example. On the same lines, we can define a general Boolean polynomial function where the polynomial p, this polynomial p can be anything and the Boolean algebra B can be any Boolean algebra, but the mechanism remains the same for defining a Boolean polynomial function. So if b, coming to the definition on the left, which is, or left of the screen, which is the general definition of Boolean polynomial function, if b is any Boolean algebra and p is any Boolean polynomial over the set of n symbols, let's say x1, x2 and so on till xn, which we are denoting by capital X, then the Boolean polynomial function, which we denote by p bar b, is a mapping from Bn to B. In the domain Bn has to be taken because there are n symbols over which the Boolean polynomial p is defined. These n symbols are x1, x2 and so on till xn. So that is why in the domain of p bar b we have Bn, and p bar b maps every element of Bn to an element in the Boolean algebra B. Now the element in the domain, which is Bn, are going to be n tuples where of the form a1, a2 and so on till an, where a1, the first component, would come from the Boolean algebra B, the second component would come from the Boolean algebra B, and the nth component would also come from the Boolean algebra B, and everything, the whole n tuple, would be taken to some element in B. P, and the image of this n tuple is going to be p bar B, a1, a2 and so on till an, where this is going to be an element in B. And how will this element be obtained? This element p bar B, a1, a2, an will be obtained by replacing in P wherever in P there are these n symbols, x1, x2 and so on till xn are coming. So wherever x1 will come in P, it will be replaced by a1. Wherever x2 will come, it will be replaced by a2. Wherever xn will come, it will be replaced by an. And using the rules of Boolean algebra, the correspondingly the value of p bar B, this a1, a2, an will be calculated after the replacements are done, just exactly in the same way as in this example. X has to be replaced by the first component, which is a1, and y has to be replaced by the second component, which is a2. In the same way, the value of p bar b on the left, the value of p bar b, a1, a2 and so on till an, can be obtained by replacing these n symbols by these n values respectively, a1, a2 and so on till an, and using the rules of Boolean algebra. So this is the general definition of the Boolean polynomial function, which corresponds to any Boolean polynomial p over any Boolean algebra B.